Across the planet, entire landscapes are getting wiped and rebuilt. Fields, suburbs, and open lands, all turning into AI data centers almost overnight. And each new one is bigger, pulling more power and water. The scale keeps rising, but the physical limits stay put. Silicon and electrons carried us as far as they could, but the gap can only be closed by an entirely new technology. It is the hottest problem in the industry today, and the search for a solution is triggering for a new gold rush. I'm coming from chip design, and in this industry it is quite rare that you see a shift that big, and even more rare that you can explain it as it happens. So today's episode, which is my first episode, we will cover 3 key innovations that form the blueprint for how AI data centers will scale over the next 2 decades. Subscribe to the channel and let's get to it. A single next generation AI campus draws 1 to 2 gigawatts of power. That is the same order of magnitude as an entire metropolitan area. In some regions like Virginia, data centers already swallowed a quarter of the grid, and we are still just getting started. Inside these buildings, millions of GPUs crunch data and dump heat into the air, and once this heat hits the room, it has to be pushed away just as fast. Almost 40% of the total power inside a modern data center doesn't go for chips at all. It goes straight into cooling, eaten by giant chillers humming in the background. The real problem is not even this massive compute. It is the sheer volume of data being moved, because we are simply moving too much data, and we are doing it wrong. AI data centers are not normal. They are something entirely different. Take Meta's Hyperion project in Louisiana as an example, which is the largest AI data center ever attempted in North America. Hyperion is not a bunch of computers together. It is a massive computer, which is the size of Manhattan. Over 1 million GPUs are inside it, and they are all together acting as single AI supercomputer. When a single workload spans an entire building, every link delay becomes a choke point. Here, the network is the computer, and at the center of all of it is copper. For decades, copper was perfect, but today it holds us back. At modest speed, copper can carry signals for meters. At AI speeds, it shrinks to inches. To keep the signal alive, you stack amplifiers and retimers, and each one is burning more power. At some point, you may double the processors and see no speed up because the copper network is suffocating them. The only medium left with enough runway is light. Once information rides photons, all the old constraints fall away. Light doesn't grind through resistance, and it doesn't spill heat, and it's like switching from a car stuck in traffic to a magnetic train gliding on rails. And optics is already everywhere, under oceans or between racks, but it is missing from the most important place, which is the last 2 centimeters next to the chip. Bringing optics to the chip sounds simple, but it was a physics nightmare. Look at this device, which is a modulator, which turns data into light. Some are huge and others are tiny, but they drift with the slightest temperature change. A 2-degree shift knocks them out. Meanwhile, GPU can jump from 30 Celsius to 90 Celsius in seconds. Skeptics said, how can you put something so sensitive next to something so hot? And for 20 years, this where photonics failed. But one Belgium group refused to give up, which is Imec. They knew silicon is great for logic, but terrible at emitting light. And gallium arsenide is great for light, but you can't grow it on silicon because it cracks. So Imec tried to find a hack. Instead of forcing a layer on top, they carved tiny V-shaped trenches into the silicon and grew the gallium arsenide inside those channels. The walls trapped the defects and it worked. Then they said, now we can start printing lasers on silicon. But we still need a modulator that can survive the heat. The trail led to silicon germanium. It reacts fast and stays stable under heat. Imec spent years fixing this mismatch, layer by layer, until they built a device that pushes 440 gigabytes per second, which is double the industry standard, with a fraction of the power. This breakthrough triggered a gold rush, and then Celestial AI went all on germanium, and Marvell bought all of them for over than $3 billion. And also TSMC is building COPE technology, staking photonics right on top of electronics to handle the whole pipeline in one package. But the most interesting company, Lightmatter, because they are building Passage, which is an optical layer that sits under the processors, which let chips outside world using light. Every chip gets its own fast or its exit lane, while others announce 8 terabytes. Lightmatter is hitting 64 terabytes per second, and because it's integrated, it costs way less than buying thousands of pluggable cables. It's clear that the future of AI factories will run on light, not copper. And if you zoom out, every jump in human civilization came from two things: better ways to compute and better ways to move information, writing, transistors, and now AI is the next layer. Copper got us to the smartphones, and light which will push us to the next milestone of humanity. Optics is the real continuation of Moore's law. And finally, if you enjoyed this video, don't forget to like, subscribe for the next episodes. Thank you for watching and Happy New Year. See you.